Hello, everybody. Good afternoon. Hello, Adam. Hello, Caleb. Hi. Microcomputer systems. Destination and source for divisions. Okay, so it's 2:15. I think we can slowly start. Will the second part of microcomputer systems cover all 200 pages? Of course. No, no. The lecture notes are for a bigger lecture with more SWS with more hours per week, and therefore I guess that we cannot cover all of the topics. I will focus on the most relevant ones from my perspective, and we will simply skip the remaining chapters. But you will recognize this. Yeah. So I give you a hint which chapters are relevant and which chapters can be skipped. We've already skipped some pages in the past, and I will do also so in the next weeks. We cannot cover everything. Okay, then we start with our today's lecture. Welcome everybody. Microcomputer technology on this Thursday. The weather outside is not so good. It's cold and foggy here. Yeah, outside of my window, my office window. Therefore, it's a good day to do some microcomputer related topics. Yeah, so going for a run is also a good idea today. So today, what I want to do, we start with a short repetition to go back on track. In the last week, we have discussed some of the arithmetic and logic operations that can be implemented using our ARM instruction set. And in the lab yesterday and in the last week, we have already done some practice with this assembler coding. We have implemented two easy problems. One XOR, one exclusive OR, and one AND operation. And today we want to go ahead with branching and looping. This is very important because you know from your programming class that real-world programs always need a branch. Otherwise, your program will always repeat the same steps. So there is no dependency then between your program and user input. So you need an if statement or something like this, a conditional branch, to make a decision between two or more options. So from C or C++, you know if or if else or switch case to make a selection between different options. And of course, we need this branching here too in our assembler language. And we will take a look at loops, at looping. So repeating the same instructions again and again until we have reached a specific condition, and then we will leave the loop and we'll go ahead with the next instructions. And you will see that on the hardware layer, on the machine layer, a loop needs much more effort to be realized, because here we have to handle with memory cells, with hardware addresses, and the convenience that is offered by your compiler to you is not available here. But we will see step by step today, and we'll try to understand how to implement this. So let's start with a simple comparison. A comparison is required in the next step to do a branch, to make a conditional jump between two options. And the mnemonic, the command that we use to compare values, is simply CMP. CMP for compare, and the manual gives us the information that we compare, or that compare subtracts an immediate value from register value. It updates the condition flags based on the result and discards the result. So what does this mean? In the end, we can write, for example, compare R3 immediate 5. We can compare R3 with immediate 5, and then our machine code or our assembler will simply subtract immediate 5 from the content of R3, will update the flags, and then the result of the subtraction is discarded. Yeah? So it's not used, R3 is not updated, and this is comparable with a simple if statement. And for example, the variable a is stored in the register R3, and the variable b, that's a storage location for our immediate 5. And so we can compare a and b, and after the comparison, in this special case, if you only write compare and no other command, no next instruction, then this is an if a equals b and an empty branch for true. So nothing will happen. So this statement alone only compare a register with an immediate value that will not have any effect. It will update our flags, so zero flag and sign flag, negative flag, but it will not do any branching or decision. So therefore we need another command. And this is shown on the next slide. Let's see the right one. Yeah, we can also use compare with two registers, Rn and Rm. Then we make the subtraction between the two given registers. So you can use an immediate value, you can use a register depending on your use case that you want to implement. Okay. So compare. Compare alone has no functionality, but we want also to do some branching between different options. So one branch for true, one branch for false, and this is realized via the B command or the B instruction.
Today,
and
this is our online class
the
for
branch
all
instruction,
students.
I zoom in a little bit, it's a little bit small. The branch instruction, B for branch, causes a branch to a target address. So you will see an example in a few seconds. You will write something like branch, C is a condition, I will show you the condition in a second, branch to a specific label. So with branch, you can make a jump to a specific label, and this is comparable to a goto statement in C or C++. Have you seen the goto statement in your programming class? I guess yes. Yeah, you've seen it. Huh? Your prof told you that with GoTo, you can jump to an arbitrary line of code, to an arbitrary position in your source code. And the same functionality you will find here on the machine level, because the GoTo is a direct abstraction or a direct derivation from the machine level. And your prof, I'm sure, told you GoTo works, but it's not the best way to organize your code. You should write structured code. You should only use conditional branches, and you should use loops. So while, do while, for, whatever. And you should not use GoTo, because your code becomes hard to read and hard to maintain, hard to adapt to new requirements. Here on the machine level, we have no structured components like while, for, if, switch, and so on. These instructions are not available. We have to realize everything with a jump to a specific address, with a branch to a specific address. And therefore, we have this statement, this instruction B, but you cannot write B alone. B is simply an unconditional branch. So you always jump to a specific label. You have to, or oftentimes you have to use an extension to B. This is shown here with this C in angle brackets. This describes the condition that you want to check. And the conditions are here on the left side in this table. So for example, if you want to check for equality, A equals B, then you have to write BEQ. So the two letters here are an extension to the B on the right side. So you have to write BEQ for branch equals. And this is equivalent, of course, in C++ to two equal signs. A equals B is A equals B in C++. This means you are checking for equality. And the conditional flags that indicate equality is the zero flag. The zero flag must be 1. Why must the zero flag be 1? So you can remember on the previous slide, we have seen the compare statement. So we can write, for example, compare R1 immediate 2. Then the compare will subtract from the content of R1 2 and discard the result. If R1, if the content of R1 is the number 2, then 2 minus 2 gives you a 0, and then the 0 flag is updated, right? So if the content of R1 is a 2, then if I write in the next line branch equal to a specific label, my label, then this branch will be executed. So if R1 contains a 2, 2 minus 2 is 0, then the 0 flag is updated, and therefore BEQ will realize a jump to the label my label. So here the flag, the 0 flag is required. The 0 flag is only 1 if and only if the register and the immediate value, so the two values that I have compared, have the same value. Therefore, we've got here in the column conditional flags, we have set equals 1. We can also check for branch, for non-equality or not equal. So if we write BNE, branch not equal, then we check if the 0 flag is 0. If the 0 flag is 0, then the subtraction of R1 and 2 gives us not a 0. So R1 and 2 are different, and therefore set equals 0, and then I can branch to a specific position. So now you can see here on the right side in the column conditional flags, you can always see which flags of our APSR are checked for this specific condition. Now that's an additional information. As programmer, in the end, we don't need it because we simply state branch equal or branch not equal or branch greater than or something like this. But your control unit, your CPU, needs a flag or needs a marker to decide, okay, should I branch or not? And the only markers, the only signals that can be used are the flags in our APSR. There are no more indicators that can be used. Yeah, then we can branch for a lot of different conditions. So, for example, we can branch if the carry bit is set. Carry is set if I made an addition and there is one additional one that has to be stored because the numbers are too big for our registers, then I can branch for carry set or for carry unset. I can branch for a negative number, for a positive number, and so on. So here are a lot of different possibilities, but here at the bottom are the one that we oftentimes use. So we can branch for equality, inequality, and we can branch for greater or equal. We can branch for less, we can branch for greater, and we can branch for less or equal. Now these are the direct corresponding operators in C++, and in the mnemonic code we have to write BGE for branch greater equal, BLT for branch less than, BGT for branch greater than, and BLE for branch less or equal. And now we have all operators that you also know from your programming class, but the main difference is that we need here two statements. We need one statement to realize the comparison or to modify, for example, the carry flag. And afterwards, we need a specific branch to go to a specific memory address or a label. Okay. There is one additional command for branching that can be used directly, BL. BL stands for branch with link. This is used if you want to invoke a subroutine in your assembler code. Yeah? So sometimes you have split up your code into dedicated parts, into dedicated subroutines that can be invoked from different positions. And like in C or C++ or Java, if you want to invoke a function, you need a special instruction, and the instruction here is BL for branch with link. We'll see an example in a minute. Okay, so this is the table for the operators that can be combined with branch. And now I think an example is a good idea. So here on the next slide, we want to transfer the given C code, this for loop, to the corresponding implementation in assembler code. So the for loop here at the top uses an integer variable I, initialized with 0, and as long as I is less or equal to 100, the loop counter is incremented and the loop body is empty, so nothing is done. So this loop simply increments our integer I and no real operation or no real loop body is done here. But you will see that here at the bottom, we need 1, 2, 3, 4 assembler instructions to realize the same functionality in assembler code. That must be the case because a higher level programming language offers you abstraction, so you can easier state what you want to execute or what you want to do. And if you go down to the hardware, this abstraction level is reduced again, and therefore we need more instructions to realize the same functionality. So the higher the abstraction, the shorter the programs become, and vice versa. Okay, so let's check what's going on here. I try to mark for you what I'm talking about. Yeah, we have some ellipses here for additional instructions. So before the for loop, after the for loop are additional instructions. And then we start with a move command and we copy the immediate value 0 to our register R4. So the register R4 stores now the value 0. This value, this is in the end our loop counter. So you can take a note here if you want. This register stores our loop counter I. Then we put a label here. I've told you a label is simply a marker in our source code to name or to select one specific line. And here I use the label name label1. And important are the colons here, right? The colon is important because this is the identifier for the label. So here, this is simply a name. You can use every name you want, coffee, beer, tea, whatever you prefer, but you need a colon to mark this specific line here. Okay, and then we start with the next operation. We make an addition. We make an addition of R4 plus 1, and we write the result back to R4. So this line makes an increment in the end, an incrementation of our loop counter I. Right here I plus plus for you as comment. So we increment the loop counter. And now we compare R4 with immediate hexadecimal 64. Why hexadecimal 64? Because hexadecimal 64, this is 100 in decimal, right? So we have 6 times 16 power 1. This is 6 times 16. This is 96 plus 4. This is 100. So here we make a comparison of R4 with 100. So in the end here, a subtraction is done, the flags are updated, and the result is discarded. So R4 is not modified with this command. R4 simply stays the value. So for the first iteration, the value 1. And then we make in BLE. What's BLE? BLE stands for branch less or equal. So if I take a note here again, less or equal, you see that's the same operator like here on the top, less or equal. And if the last comparison is less or equal, so if R4 is less or equal than 64, then I make a jump to label 1. So as long as R4 is less or equal than 100, I make a jump to label 1, and then the next iteration will start. Bacon, lettuce, egg. Is this your name for the label? You can also use this if you want as label. Okay. For BLE, okay, now I got it. That's BLE, bacon, lettuce, egg. Okay, I think that was your label name. You can also use bacon, lettuce, egg for a label name, but then you have to write a lot. Okay. Yeah. So you have missed your lunch, Adam. That's not a good idea. Going into a lecture hungry. Okay, bacon, lettuce, egg, very nice. Okay. So BLE, we make a bacon, lettuce, egg to label 1. And to label 1. And then we start with the next iteration. That means we make I++. So we add 1 to R4. We make a comparison again. We will recognize, okay, 2 is still less or equal than 100, and we make a branch. So this is the iteration. Iterate like this. And the loop body is empty. Loop body is empty. We have no commands that are executed for each loop iteration. If I add some commands here in the parentheses here, where I have to write the commands here in my mnemonic code, where to add which line? What do you think?
Before the BLE.
Before the BLE. So you mean here, right? Here in between. So yeah, it's okay, but there's one small detail that you have to.
The flags would be.
Yeah, Adam?
Yeah, so the flags would have been updated with their compare. So it would have to go before the compare.
Yeah, you can.
Because the BLE uses the flags to function, right?
Yeah, right. But the problem is, if your commands are first, and then is your loop counter checking and increment, then this means that you always will iterate at least once, right? This loop here, this example, this direct translation will always do at least one iteration. And you know from your programming class, the for loop does not work like this. The for loop is, in German we say kopfgesteuerte Schleife. Direct translation would be that's a head controlled loop. So this loop, this looping condition here in the header may also decide not to loop at all. But if you implement it like this, with first the label, then the checking for the loop counter, and then you put the commands in between, then you have realized a do-while loop. Right? The do-while loop will realize at least one iteration. It's not relevant how the loop condition will evaluate, one iteration is done. But the for loop can also break directly, so it cannot execute the loop body at all. So you cannot simply add here the commands, it becomes a little bit more complicated. So you have to change the logic. You first have to check for the loop counter, and then if the loop counter is valid, then you go ahead. Then you go ahead. Otherwise, you simply skip everything. And here at the end, you again check for the loop counter. So please don't try to fill in here commands. It will not work. It's not exactly the same semantics. So this is only the example to show how to work with the loop counter.
So we'd have a label 2 up at the top and skip down. Okay.
Exactly. So you can introduce another label to skip the entire loop body if you need it. Correct. Yeah. So maybe take a note that the implementation shown is more a do-while loop than a for loop, but it's correct because it simply translates the code from the top here to a sample. And you see here, you need more instructions, more commands to execute or to increment a simple loop counter. And this is in the end, this BLE, this is a go-to. This is a go-to. And now you get a feeling that it becomes much more complicated if you have a program with a lot of branches, a lot of loops, and you have to translate everything to B commands and corresponding labels. So it becomes a deeply nested structure of labels and blocks. So that's not so easy to directly translate, but here the compiler, the cross compiler helps you. So it takes your C code and generates some machine code for you. So that this as first example. Is this clear to everybody what I've told you?
Yeah, it's clear.
Okay. Then we take a look at the next slide. This is the same example from the previous page, but Lucas, you've got a question?
No, sorry.
No problem. So that's the same example as the previous page. The only difference here, we have also given the memory layout. So how this is written to the main memory of your machine, of your ARM machine, and how the execution is done. Here on the right side, we have again our mnemonic code. So move, add, compare, branch less equal. And you see here that for the mnemonic, we can write a label, but of course, after the mapping to the machine, there are no labels anymore. The labels are for the programmer to make the work easier, to outline which position I mean in my code, but there is no label or no bacon, lettuce, egg within the code. So I have to count the addresses, and this is shown here. So if I want to branch, then I have to tell the control unit branch to which position. And which position means which memory address should be used. And this is expressed via an immediate value, in this case, -4. -4 means if BLE is reached and BLE is stored in this memory address, hexadecimal 1125A, and I subtract -4, then I go back 4 memory cells or 4 addresses, and then I reach hexadecimal 1125 and 6. And at this position, I've got again my add instruction. So the branching means on the machine level, on the lowest level, that I have to outline to which memory address the jump should be realized. So I can jump backward with negative numbers. So for example, -4 instructions or -4 memory cells, and I can also jump ahead with +10 or something like this. But I have to count in the end the addresses. I have to count the memory cells. So therefore, it's relevant how many bytes are required to store each command. I've told you that there are commands that only need 1 byte, 2 byte, 3 byte, depending on the instruction set. And of course, if I use a command that needs more bytes to encode, then my entire memory layout will change. So the branch will be at a later position. So I have to branch more lines backward or ahead. So the memory cells are relevant, but yeah, it's a little bit annoying because we really have to count. We have to count the lines in the memory to select a specific line. So it's a little bit annoying, and this is supported by the compiler. So we can write mnemonic with labels, and the labels are replaced with the corresponding number of lines that I want to go backward or that I want to go ahead. Okay. So here is another example from an exercise sheet. We'll see if we cover this also in the lab. Yeah, on this page, what's important? Let me see. Yeah, there are some additional commands here that we have not discussed. So, for example, here is an NOP command. An NOP command, or NOP, stands for no operation. No operation, and you know from your programming class, sometimes you have to put a semicolon for an empty instruction because you need an instruction, but you don't want to do anything. And then in C++, you simply put a single semicolon, and this is an indicator for nothing should be done. And nothing should be done can also be stated here in assembler. This is always a NOP command, no operation. So do nothing. And we will see in another example in a second that sometimes no operation is necessary because your CPU cannot be stopped or halted. You cannot shut down your CPU. The only chance to stop your CPU is to power off the CPU. Then the control unit will stop and nothing happens. But as long as your control unit works, so as long as your PC is switched on, your control unit and your CPU is always calculating. And it's like the human brain. So you cannot not think about something. You're always thinking about something, and your brain is always working. You cannot say idle or stop. So you cannot stop this process. Your brain is always working. Also during sleep time, you are dreaming because your brain is not able to stop this process. And the same is for your CPU. The CPU cannot be stopped. And therefore, if you want to do nothing, your only chance is to do actively nothing. And for actively do nothing, you have the no operation command. So you can idle, 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 idle until a new task arrives. And then you execute a new task. And after completion of the task, your CPU is still switched on, but there is no work. So you are idling, 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 idling. So you need a command to actively do nothing. So that's procrastination. Procrastination for your CPU, waiting for some new task. Yeah. That's the no operation command. Yeah. Okay. So maybe we'll see this in the lab. We skip the details for now and go ahead to the remaining instructions that we want to know. On the next page, we see some shifting operations. Shifting operations are very important because we can do or we can solve a lot of tasks only with shifting to the left or shifting to the right. And the command for a left shift is labeled LSL, logical shift to the left, and the command for right shifting is named logical shift to the right, LSR. And here at the bottom, we have an example how LSL and LSR works. We have again our register R2, and in the register R2 we have this big pattern, this big sequence of ones and zeros. This is stored in our register R2. And now we give the green instruction here. We state LSLS. That means logical shift to the left with update of the flags. So left shifting with updating of the flags of the register R2 by one position, and the result should be written to R5. So we can make a shifting operation based on register using a specific number of positions, and then the result is written to another register. Here in this case, we are shifting R2 and we are writing the result to R5. And the shifting is shown here by the green arrow. You see that this 0 here is moved one position to the left. This one is moved one position to the left. This one is moved one position to the left. This 0 is moved one position to the left, and so on. So all bits within the register R2 are shifted one position to the left, and on the rightmost position, we push in another 0. That's all. That's a left shift with using one position, and the result, the green result now, is written to R5. Of course, we can also do a right shift. A right shift is shown here on the bottom with the orange instruction, LSRS, logical shift to the right with updating of the flags. We are using register R2 again, and we use 3 positions for the right shift, and we write the result to the register R3. So now we again use our register R2. R2 has still the same value, and we shift this one 3 positions to the right. So 1, 2, 3. Then we shift this 0 3 positions to the right. We shift this one 3 positions to the right. We shift this one 3 positions to the right, and so on. So all bits are shifted 3 positions to the right. On the left side, zeros are pushed in, and then the result is written back, in this case, to R3. This is the shifting operation. So, okay, we can shift left, right, but what's the purpose? Do you have an idea what I can do with a shift operation? Which operation can be realized by left shift or right shift? No idea? Then we take a look at our binary numbers again, and then I'm sure that you see the possible usage. So let's do some binary arithmetic again. We have the decimal 5, and the decimal 5, what's this in binary? Decimal 5?
101.
101. So this is 4 plus 1, right? This is binary. And now I want to multiply 5 times 2. In decimal, this is a 10, right? We directly see this is a 10. And this is decimal. And now we want to do the same. We want to do the same in binary. We want to do this multiplication. And this multiplication in the end, 1, 0, 1 times, what's 2 in binary?
1, 0.
1, 0, exactly. It's a 1, 0. And now if I want to do the multiplication, I do it like in decimal system. I've got 1 time 1, 0, 1. So I get 1, 0, 1. And I've got 0 times 1, 0, 1. So I get a 0. Then below the line here, I got the addition. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. So this is 1, 0, 1, 0. And this again in decimal, what's this?
10.
That's the 10, exactly. So, and now if you compare our initial 5 and our initial 5 and our initial 10, then you see that the 5 or the 10 is 1 additional 0 at the right side. This 1 additional 0 has been introduced by the multiplication with 2. If I multiply not with 2, but I multiply with 4 times 4, then I multiply with times 1, 0, 0. And if you repeat now the multiplication, you will see that we shift in 2 zeros at the right side again. So a left shift corresponds, left shift of 1 position corresponds with the multiplication with 2. So this here, the green operation here is in the end a multiplication with 2. If I left shift 2 positions, this is multiplication with 4. If I left shift 3 positions, this is a multiplication with 8. If I left shift n positions, this is a multiplication with 2 power n. So a left shift of n positions corresponds to a multiplication with 2 power n. And of course, it also works in the opposite direction. A right shift of 1 position corresponds to a division by 2. And a right shift by n positions corresponds to a division by 2 power n. And this is a way to do multiplication and division for base 2 very, very fast. You simply have to push in zeros at the left side or at the right side. So therefore, shifting operations are very, very performant, and you can do multiplications, divisions with by 2 very, very fast. By the way, as a short reminder, you can also do this in C or C++. What's the operator for a left shift? What's the operator for a right shift? You can write it to the chat, or you can also say it, of course. Who can remember? No? Nobody? Then I write it here on the slide. Left shift is smaller, and right shift is greater. So the angle brackets, double angle brackets to the left, to the right, is a left shift or a right shift. So you can write in C++ the same. You can write I, that's our variable I, left shift let me 2 like this, or you can write I equals right shift 2 like this. This is left shift, right shift, and direct assignment. Now, of course, you can do it. In 2 steps. You can also write I equals I left 2, I equals I right 2, something like this. This is also possible, but you can also use it directly with an assignment. So if you want to divide or multiply by with 2, do it with a shift. It's pretty fast than do it with a real division or a real multiplication. And most compilers will replace your multiplication and your division with a shifting operation. So during the code optimization step of your program, sometimes the compiler replaces with a better operation, with a faster operation. Okay. Questions? Or is everything fine? Okay. Then we have nearly done. Now we have a bigger example. And this is the level where the exam will take place. Yeah? So this type of code or this complexity of code, this will be part of the exam. And with this JSLite, you can do a lot of nice exercises. You can modify the JSLite, you can use different patterns, and therefore oftentimes or sometimes you will see a similar exercise in the exam. So this is now very important. So everybody tired now should wake up. Now it becomes very important. And I explain you now the JSLite. Okay. You know the JSLite from Knight Rider. Do you know Knight Rider? David Hasselhoff, Knight Rider.
Yes.
Old school TV series. So I guess there is a new version of the series, and I'm not sure, but I think there is also a new one. But the original one was with David Hasselhoff back in the 80s, something like this, very old. So it's not the perfect series, but there is a talking car. The car is named Kit, and the car was artificial intelligence and can drive very fast, and it can talk, and it can do everything. A very nice car, and the driver of the car was David Hasselhoff. And you know David Hasselhoff, he also can do everything like Chuck Norris. And then David Hasselhoff drives around and solves some cases, criminal cases or something like this, and tries to help people. Yeah? So that's the entire story. And now you know everything about Knight Rider. And in the front, under the hood, or in the front of the car, in the, what's the English term, Kühlergrill. So between the two lights in front of the car, there was a JSLite. There were 4 or 5 LEDs, and then the light moves from left to right, from right to left, from left to right, to indicate that Knight Rider is alive. The car Kit is alive, And this chase light is used also today. For example, if you go to the airport and take a look at some information tables, then you will see LED matrix displays. And then sometimes you see some writing that moves from right to the left, or some patterns to indicate some information. And these are in the end all chase lights. So the idea is this red, we have 4 LEDs like KIT, and then the rightmost is switched on, then this one is switched off, the second one is switched on, then this one is switched off, the third one is switched on, then it's switched off, then the last one is switched on. And if I've reached the left side, I again move to the right side. So I switch off the fourth one, switch on the third one, switch off the third one, switch on the second one, and then I loop and go back to the first position. And if you do this fast enough, you will see the movement. You have a moving light from right to left, from left to right, from right to left, left to right. That's Knight Rider. And now your task is to implement this movement. You have to implement the chase light of KIT, and the code is shown here in C syntax and in assembler code, and we try to figure out how it works and how we translate between the two implementations. So let's see if we can do this. We first try to understand our C code, because we are more familiar with C code. So we start with an integer variable LED. The integer variable LED has the value 1. This variable, this LED, stores the position or the number of the LED that should be switched on. And this LED has the value or the address 2 power 1. The next one has the address 2 power 0, sorry, then 2 power 1, then 2 power 2, and 2 power 3. So the LEDs are addressed with 1, 2, 4, and 8, the powers of 2. And because we want to start at the right side, we use for our LED the value 1. And now we start with our movement. We have an infinite loop, a while loop. While 1 means while true, infinite loop. And within this infinite loop, we have 2 nested while loops. You can see the first while loop is iterating as long as LED is not equal to 8. Not equal to 8 means we have not reached the leftmost position, because the leftmost position has the value 8. And as long as this is true, we have not reached the leftmost position, we invoke the function right LED with the specific number. Right LED is a subroutine, not shown here, but it is used to switch on a specific LED in our chase light. So we switch on LED 1. And after we have switched this on, we make a left shift of our LED by 1 position. This is the syntax from C I've mentioned on the previous slide. So we make a left shift of LED by 1 position. So we multiply 1 with 2. So we get a 2 here. So we get a 2. Then we wait for a specific time. Wait simply interrupts the execution for a defined time. So for example, for 1 second, 2 seconds, whatever, because otherwise the chase light will move so fast that you cannot see it. It's too fast for the human eye. So maybe you see some flickering, but you cannot see the movement. Therefore, we need here another function to wait for a specified time. And then we do our next iteration. how many iterations will this loop realize? How many iterations?
Three.
3 or 4? Helen says 4. So we start with 1. 1 is not equal to 8. Then we increment 1, or we left shift 1. So we got a 2. 2 is not equal to 8. We do another iteration. We get 4. We do it. 4 is not equal to 8. So we do another iteration. Then we get an 8. 8 is equal to 8, so we break. So we are doing 4 iterations or 4 steps. And then we leave this loop because we have reached this position here, the leftmost position. Now we are here. Okay, so from the leftmost position, we enter the next while loop. The next while loop checks if LED is not equal to 1. The LED is not equal to 1. The LED, if we leave the first loop now, has the value 8. 8 is not equal to 1. Therefore, we write the LED. Then we make a right shift by 1 position. A right shift by 1 position. So the 8 becomes now here 4 again. We wait for a specified time and we check again. 4 is not equal to 1, so we enter the loop again. We write our LED. We make the next shift to the right. We get a 2. 2 is not equal to 1, so we make another iteration. Then we produce a 1, and for the 1 we will break. For 1 we will break. And then we leave this loop, and because this loop is contained into the infinite loop here, we start over here at the top. And now we are at the rightmost position again, and now we move our LED, our chase light again, from right to the left. That's the implementation in C. Okay.
Sorry, Professor, what does the line of right LED bracket LED do again?
The right LED, this is the function to really switch on one position within the chase light.
Okay.
Yeah, so we need another function that realizes an access to the hardware and to switch one pin for exactly this LED on or off. And this is right LED. Yeah, this is the code level for the X. Therefore, I told you, wake up. This is an important slide. Okay. So this is the C code. So we don't need to know how right LED works or how wait works. This is given to you. It's part of, so to say, your library. You can simply use it, but you need to understand the structure of the program. So I think the C part is clear. And now we need a translation of the C implementation or the C code to the assembler code. This is shown here on the right side. Okay, what's going on? First of all, we store a 1 in register R0. R0, this is our variable LED in the end. So LED and R0 have the same purpose here. Yeah? So here we have our loop counter and we start with a 1. The next line we have label loop 1, and then we have the instruction branch link write LED. This branch link invokes the function write LED. It's the same like here on the left side. On the left side, you simply write the function name and the parameter. And here on the right side, we simply make a branch to write LED. And this write LED knows that it should use register R0. So there is a connection between the subroutine and the main routine. of course, defined by the programmer, but we cannot see it here. Yeah? So write LED, the subroutine, must take a look at R0 because it needs the current value of the loop count. Okay. Then, after we have switched on the LED, we make our left shift. We left shift R0 by 1 position, write the result back to R0, and we wait a small period to make it visible to the user. Therefore, we branch link to wait. And now we have our first comparison. We are comparing R0 with immediate hexadecimal 8. So we check if R0 and 8 are the same, have the same value. If in R0 we've gotten 8, then branch not equal will be false. Then we skip this command, but as long as R0 is smaller or not equal to 8, this means not equal to 8, we jump back to loop 1. Then we again make an iteration, so we make a left shift. So we've got 1, 2, 4, and then we've got a break. 1, 2, 4, and then we've got a break, and so on. This is the first loop. The second loop, or the next instruction, is executed as soon as branch not equal is false. So as soon as we have an 8 in R0, we go ahead to loop 2. And in loop 2, we have the same structure. We branch link to right LED. We make a right shift of R0 by 1 position. We wait a few seconds, and then we compare R0 with 1. This comparison means now, have we already reached again the rightmost position? If we have not reached the rightmost position, so if branch not equal, if both are not equal, then we jump back to loop 2 and we iterate again. So we make 8, right shift 4, 4, right shift 2, 2, right shift 1, terminate. And then we are here in the last line. In the last line, we have only a B. Only a B means simply branch. Branch without condition. And we branch to loop 1 again, and loop 1 is here at the top. So the first loop means move from right to left. If I've reached the leftmost position, I enter loop 2. Loop 2 moves the LED from left to right. And as soon as I've reached the rightmost position, I jump back to my first loop and do another iteration. This infinite loop here at the top, this while 1, this is realized by this B. Simply B means branch always. And if I always branch to a previous position, this is an infinite loop, because then I've got an infinite loop. Okay. So a lot of errors here now. Okay.
So does the branch link command automatically put us back to where we left off when that branch is completed?
When the branch is completed, then the next line of code is executed.
Yeah, but for the branch link, so we branch link to a label called wait.
Yeah.
And so that'll have a timer in it.
Yeah. Yeah.
And then, but we don't have to reference where we left off. It'll bring us back here automatically.
Yeah, it brings you back to the next position here.
Okay.
Yeah. So the branch link under the hood realizes some more additional steps, because if you invoke a subroutine, you have to save your current state. So the current state of your control unit must be saved for further execution. So if you invoke branch link, then for example, your APSR, your status register is stored on the stack. So there is made a copy on the stack, and also all used registers are stored on the stack. So you got a copy, a backup of your current state. And then you jump to your subroutine, and the subroutine wait or write LED can read the backup state from the stack and can use the register values, the APSR, and so on. So here under the hood, there are additional tasks realized, because as soon as I jump back to the next line to compare, I need the state that was there before I have jumped to the subroutine. And this backup of the state is done by the branch link. So it's in the end a very complex command, because you have to make a backup of your entire machine state and then invoke the function.
Okay, thank you.
Okay. Are we free to use the method we wish to write the code with, or we shall be specified to use a particular method, C code or assembler code? Yeah, it depends on the exercise. Sometimes I give you the C code and I tell you convert this to assembler code, or sometimes I give you just the problem description and say, please write an assembler code to solve it. So yeah, these are the two options. I think from assembler code to C code again, it's not so interesting. I will not ask you for this. So I give you C code, you have to translate to assembler, or I give you a problem and you have to state the solution in assembler. Okay. So I will not ask you for C or C++ code, because that's not a programming class here, right? You have already done your programming class with Norbert Strobel, right? Okay, good. And yeah, that's all in chapter 3. Now we have seen our first real-world instruction set. The students always ask for real-world use cases, real-world applications. So if you get, if your first job will be system engineer or software engineer on the hardware layer, and your company will work with ARM boards, with ARM microprocessors, then you will see some of these commands again, of these instructions, and you've got an overall idea how you can implement or solve easy problems. So of course the real manual takes several hundred sites, several hundred pages, and you need to know more instructions and more functionality. But I think you've got an idea how assembler code looks like and where are the differences compared to a higher programming language, so compared to C, for example. Yeah, that was chapter 3, and now comes my favorite chapter of the second part. In chapter 4 now we will design and implement our own microprocessor, and therefore I will talk a little bit again about classification or criteria for microprocessors, and then we start with our 4-bit processor. We will design the ALU, we will define a register set. We will talk about the control unit. And in subsection 4.5, with the control unit, we will again see our finite state machines. I'm sure you have already missed the finite state machines, right? Oh, you have to say yes, we've missed it. And here in chapter 4.5, subsection 4.5, you will then see the cycle, the loop. Then you will see the finite state machine again that you need to implement your CPU, your control unit. And in subsection 4.6, I will show you the full circuit of the complete 4-bit CPU. My colleague told me it perfectly works, but at the moment it's a simulation. So the CPU works, but only within a simulation tool. And he still waits for a student that wants to implement this in hardware. So his idea is that we have a big information board with the registers, with the outputs, with the results. And then you can program the real 4-bit CPU with our own instruction set, and then you can solve specific problems. And everything is visualized on a board with 7-segment displays and everything realized in hardware. So if you're interested in this, you can ask my colleague Heinz Endres. He told me he waits for a student to realize this, but up to now, no student was interested too much. So if you like it, then simply ask Heinz. Maybe this topic is still open for a bachelor thesis or something like this. He told me 2 years ago, maybe it's still open. Simply ask him if you're interested. Then we talk about periphery, some selected architectures and platforms. So the last 3 subsections are extensions to chapter 4. The core part is here 4.2 to 4.6. Okay, so let's start with a short repetition. We have already seen this block diagram in the beginning of this class. It shows the detailed structure of a microprocessor, the internal structure of our CPU. We have already seen that we need a control unit, a CU, to drive the entire processes in our CPU. And the CU is connected via a bus system to our arithmetic logic unit, or ALU, to the register set, and to the interfaces. The interfaces enable connection to the outside world, to screens, keyboards, whatever. And sometimes we have an additional bus driver to connect an external bus to the internal bus. Yeah. So, for example, your CPU is attached to a main board, and on this main board you have an external bus or an additional bus used to connect the components of the main board, and the CPU bus is attached to the main board bus using this bus driver. Okay, so before we start with the layout, with the design of our own architecture, here again some aspects that we can take into account during the design phase. For example, we can design machines with different word length. So 4-bit machines, 8-bit machines, 16-bit machines, 32 or 64-bit machines. Today, we all use at home 64-bit machines. 10 years ago, we have all used 32-bit machines, and I hope we will also see in the next years some 128 and 256-bit machines. This word length, in the end, corresponds to the size of our registers. So if we have a machine that only offers 16-bit registers, then we say we have a word length of 16 bits. And here in this chapter, we will design a machine with 4-bit word length. Why 4-bit? Because it's the easiest one. Yeah? So you will see that the instruction set and also the overall architecture of this machine is very, very reduced, very, very simplified. But to understand the functionality, everything is there. It's enough. And of course, you can add more instructions to your instruction set. Then your programs become smaller. You get nicer programs with more sophisticated instructions. But then your CU becomes more complicated. And because we want to understand how the CU works and how to define the control unit, therefore we have decided to use a very easy approach. But the details, the design details, becomes much clearer with word length 4. Then we can support or we can offer different speeds, clock frequencies. In the end, that's the system clock frequency that is supported by your system. So your PC offers 3.6 gigahertz or 3.8 gigahertz. So my machine at the moment offers, let me see, 2.3 gigahertz in standard mode. That's an Intel Core i9, for example, here in my machine, 2.3 gigahertz. And you have to make a decision or a trade-off between higher frequency and, in the end, higher power consumption or higher heat that is produced by your system. And this is a trade-off. A very good trade-off has been shown by Apple a few weeks ago with the new Apple processors, where there's a very good trade-off between clock frequency and power consumption. So all reviews were very good. Power consumption and speed belong to each other. You can draw in an arrow here if you want. They are interconnected. Clock frequency, power consumption. The CPU architecture and instruction set, we will see again von Neumann and Harvard again in a few minutes, and we will see another architecture that's called Flint's taxonomy. SISD, SIMD, MISD, and MIMD. I will explain you what this means, not today, but the next week. We talk about interrupts, programmability and software environment. This is interesting. So which tools are available to work with your system? So for our 4-bit CPU, the programmability and the software environment is really bad, to be honest, because it's a simulation in a software. So we have no IDE to implement or to work with the simulated CPU, to work with the simulated microprocessor. But of course, if you construct a CPU for the real world, like Intel or Apple, and you want to sell components, like Intel, for example, then you need a good programmability and a good software solution that customers can adapt and use your processors. Otherwise, you will not sell it. Interface properties, addressing options, we will cover not in detail, but some aspects we will talk about. Memory concepts, availability of hardware and software. This is, in the end, if you take a look at the Windows domain, availability of hardware and software, Intel in combination with Windows, everything is fine. You find a tool for everything. You find several tools for the same problem. So you can decide what you want to use. If you switch to Unix, Linux, or Mac, hardware and software is reduced a little bit. And it gets better by the time, but of course, the industry standard today is Intel in combination with Windows. And last but not least, price is an aspect So if you have to count euros and dollars, then you will not buy the latest MacBook Pro full extended to 8,000 euros or something like this. You will say, okay, also with 2,000 euros, that's too much. So it's a decision also of price. Good. Then, yeah, that's a small repetition from chapter 2. Again, the Harvard architecture and the von Neumann architecture. We have already seen this. With a professor's salary, you can buy anything. Yeah, that's a joke, right? So not really not. So not in Germany, maybe in other countries. Back to the architectures, not to my salary. Back to the architecture. Yeah, Harvard architecture. We have seen this in chapter 2. We have 2 dedicated memories for our instructions and for our data. And in between is the CPU. And this architecture is a very stable and not so error-prone architecture, because it's very clear which bit pattern is instruction, which bit pattern is data. I don't have to make the distinction in my code. The distinction is realized based on the memory cell where I store the information, and it's very fast because I can do the memory access in parallel. So this is very fast and yeah, very stable architecture. But nowadays, I've already told you that the von Neumann architecture is widely used because that's the most general architecture. We have only one CPU, we have only one memory component, and it's up to you as a programmer that you make the distinction between source code and data. And yeah, in the end, we have only one bus that connects our CPU with the memory. So let me see where we stop today. We can do the word size. Yeah, I already told you the word size of a microprocessor is the size of the working registers. So we will use 4 bits, and here are some examples for 4 and 8-bit microprocessors, for 16 and 32-bit microprocessors, and for 64-bit microprocessors. And here on the right side, we have some development over the years. This is a copy from a slide from the introduction, the total number of semiconductors that are used. And this is already outdated because every year we've got new key performance indicators regarding our microprocessors. But here we can take a look at the bullet points for the different groups. So the small, so to say, small microprocessors, 4 and 8-bit, offers us only a very small instruction set. So we have to write very long programs to solve easy tasks because the instruction set is very small. They are very cheap. They are very slow, cheap and slow. And we have very low power consumption. So today they are still used, for example, in measuring and control systems. So for example, in your washing machine, you will maybe find an 8-bit microprocessor. And we also have a compiler for higher level programming languages, for example, for C. You can implement in C, and you can compile to assembler code for 8-bit. With 16 and 32-bit, we have a convenient instruction set. So our programs get smaller because the instructions are more sophisticated. We have convenient arithmetic logic unit with a lot of arithmetic functions. They are fast and also energy saving. We can process large amounts of data, and this is most commonly used for mobile devices. So not for smartphones anymore, but for other mobile devices, technical devices, we will find something from this group here. And our 64-bit microprocessors, they are built in your PC, very high performance, used for computers and workstations. So this is standard nowadays. And we have very convenient instruction set. We can support multitasking directly on our CPU. We can support different memory management systems. So in the end, for this group of microprocessors, we have already built in some functionalities from operating systems on the hardware level. So maybe you know the term hyperthreading from Intel. This was in the end, it was a marketing term a few years ago. Intel offers hyperthreading. That means threading on the cores of your CPUs, and threading is a term from operating systems. So if you take an operating system class, Electron operating systems, your prof will tell you processes, threads, and so on. And Intel simply has taken the term thread and transferred it to the hardware level. And this is neat with this bullet point here. With this sophisticated CPUs, microprocessors, we have already some multitasking and some operating system functionality directly on the hardware. Okay, so now for today we are at the end of our session. Please repeat chapter 3 again, because we need it for the lab, you will need it for the exam, and we need it as a foundation for chapter 4. And in the next week, we take a deep dive and try to understand how our 4-bit CPU works. So thank you very much for today. I wish you already a nice weekend.